Today on Quickly Quantum, Japan says it's turned on a full-stack neutral atom quantum computer named Shunkai. Is this the Moonshot program's real hardware milestone, or another operational press release with the hard error correction work still ahead? Before that, in the headlines, China's new cyber industry plan puts quantum on its 2030 priority list. A Vienna team wants to marry electron microscopes to quantum computers to save fragile samples from being blasted apart. And Infleqtion's neutral atom stock bet gets a closer look after a 157% revenue jump. Welcome back to Quickly Quantum, your daily brief on the quantum frontier. It's Monday, August 24, 2026. Let's get into it. China's latest move first. Beijing's Central Cyberspace Affairs Commission just released an action plan running through 2030, and quantum computing made the list, right alongside advanced chips, industrial software, and blockchain, as one of the frontier fields the government wants broken through. Now, if that sounds familiar, it's because this is at least the third or fourth Chinese policy document in under a year to name-check quantum as a strategic priority. That pattern alone tells you something about how central quantum has become to Beijing's messaging, even without a fresh number attached. What's actually new here? Not much, honestly. According to Xinhua, this particular plan doesn't attach specific quantum funding figures, technical milestones, or commercialization targets. So read it as continued intent rather than a fresh commitment, which tells you where the political wind is blowing, even without a number you could actually check the delivery against. The thing that would change my read is a budget line with quantum's name on it, and that's still missing. Here's a different kind of quantum computer story, one where the quantum computer doesn't compute anything, it just helps a microscope see better. Researchers at TU Wien, working with teams from the University of Vienna, JKU Linz, and the University of Innsbruck, have found a way to make electron microscopes see more while using far fewer electrons per image. Electron microscopes normally just count electrons hitting a detector one at a time, but the team is coupling the electron beam to a quantum computer, letting the electrons interact with ions held along the beam's path, so each electron becomes entangled with the quantum computer before it ever reaches the sample. That lets them pull extra information out of every single electron instead of treating it as disposable, which means a smaller number of electrons is sufficient overall. Good news for fragile things like individual proteins that fall apart under a normal beam. If you've ever wondered how you'd image something that delicate without frying it, this is exactly that problem. The paper's been accepted at physical review letters, and the next step is building the actual instrument at TU Wien's University Service Center for Transmission Electron Microscopy, where an ion-based quantum computer developed by Philipp Schindler's team at the University of Innsbruck will be integrated into an electron microscope. It's a genuinely clever idea, and also, worth saying plainly, still a lab demonstration years from anyone's biology department using it. Here's a story with a number that actually moves markets. Infleqtion, the neutral atom company that went public on the New York Stock Exchange back in February under the ticker INFQ, reported second quarter revenue of $13.5 million on August 17th, up 157% year over year, and the company says all of it organic, all of it quantum. That's the kind of growth line that gets algorithmic traders moving before they've even read what neutral atoms are. The company also raised its full year 2026 revenue outlook to $45.1 million from $43 million, and it's part of a broader quantum stock rally that also lifted Rigetti, IonQ, and D-Wave. Infleqtion's pitch is that neutral atoms, individual atoms trapped and steered by lasers instead of the superconducting circuits IBM and Google use, scale more cheaply, and its flagship scale system has reached 12 logical qubits, meaning error-corrected qubits built from many physical ones, with a roadmap toward 1,000 by 2030. Now, one more framing question before we get to Japan. Is quantum computing basically mobile phones in 1995? That's the analogy running in Laser Focus World this week. Clunky, expensive, pre-mass market hardware that's nonetheless on a real adoption curve. We haven't independently confirmed this framing beyond the one outlet running it, and I'll say what I usually say about maturity curve analogies. They're easy to build and nearly impossible to falsify, so take it as a vibe check rather than an argument. But it does capture something real about today's other stories. A Japanese lab just called its neutral atom machine operational, and a small cap neutral atom company just posted triple-digit revenue growth off a tiny base. You'll hear this same debate anytime someone bets real money on unproven hardware. Whether either of those is a Nokia brick or an iPhone is exactly the question we don't get to answer yet. Diraq posted on X over the weekend that the lab is now up and running and already testing and measuring its silicon spin qubit technology, pushing toward what the company calls utility-scale quantum computing. That's Diraq's own account of its own progress, so take it as company-stated momentum rather than an independently verified result. There's no detail yet on what's actually being tested or what the numbers look like. Still, you can think of it as a reasonable pace, from opening the doors to running measurements in short order. It's one more data point in Chicago's bet that quantum hardware clusters pull in real lab work, not just press conferences. A bet, and the neighborhood pushback against it, we'll come back to. Our main story today: does operational mean what we want it to mean? Japan's Institute for Molecular Science announced this morning that Shunkai, the country's first full-stack neutral atom quantum computer, is now running. Full stack means it's not just a chip on a bench, it's the whole pipeline, from user input down to the laser pulses that drive the hardware, the way a personal computer integrates everything from the keyboard to the processor. Shunkai is built by a team led by Professor Kenji Omori under Japan's Moonshot Research and Development Program, and it works by trapping individual atoms with tightly focused lasers, a technique called optical tweezers, then reading out the answer by photographing the fluorescent light each atom gives off. It starts with about 50 qubits, the basic units of quantum information, with the roadmap aiming for 10,000 physical qubits with quantum error detection and correction, catching and fixing the mistakes that plague every quantum computer by March of 2031. One nice detail: the machine is named Shunkai, an alternate reading of Harumi Shibukawa, the Edo period astronomer who built Japan's first indigenous calendar. The idea being that just as he mapped precise celestial motion, this machine aims for precise control of a qubit's quantum state. And neutral atoms run at room temperature, no refrigerator required, which strips out one of the most expensive, most failure-prone parts of building these machines at scale. Why should anyone outside a physics department care? Because if a room temperature machine that doesn't need a giant fridge can actually scale to thousands of qubits, that changes the economics of who can eventually own one of these things, not just national labs with unlimited cryogenics budgets. Now, this isn't a bolt from nowhere announcement. IMS set up a commercialization platform back in 2024 with 10 industry and financial partners, including Fujitsu, Hitachi, NEC, and the Development Bank of Japan, specifically to turn Omori's lab work into something sellable. Hitachi built Shunkai's software stack, the quantum processing unit stack, the QPU, essentially the hardware brain of the machine, came from Infleqtion. Yes, the same neutral atom company we just talked about with its NYSE ticker and its fast-growing revenue. It's the same modality, the same global race, turning up twice in one episode. And John Martinis, the physicist who led Google's 2019 quantum supremacy demonstration, has already praised the underlying physics, saying Omori's team made a major breakthrough to overcome the weakness of the neutral atom method by using ultra-fast lasers to drastically accelerate its 2-qubit gate by 2 orders of magnitude. 2 orders of magnitude, in plain terms, means a huge jump in speed, a real fix to neutral atoms' historic weak point, which is that moving atoms around to entangle them takes time, and time is exactly what a fragile quantum state doesn't have. Partner company Yakumo had actually targeted this system to be operational by the end of 2025, so today's news lands close to schedule, just a few months late. And Shunkai isn't stepping into an empty room. It joins a genuinely crowded neutral atom race. Q-Era already has a machine running at Japan's own AIST Institute, with roughly 37 logical qubits built from about 260 physical ones, and Microsoft and Atom Computing have their own neutral atom system, called Magni, chasing the same early error-corrected milestones. 3 well-funded teams now say neutral atoms work: Q-Era at AIST, Microsoft and Atom Computing's Magni, and now Shunkai. The open question is which one gets to trustworthy error correction first, and which one anyone outside the lab can actually rent time on. So how much of this is real progress, and how much is press release choreography? Let's start with what the scientist actually says. Professor Omori himself, in the IMS press release, put it this way: neutral atom-based quantum computers have recently been rapidly attracting attention around the world as a new modality that could exceed the limits of the superconducting modality, which started its development earlier. I think it is extremely significant that now we have developed Japan's first full-stack quantum computer in this cutting-edge modality and started its operation. That's a scientist marking a milestone he's spent years chasing, and I don't doubt the sincerity of it. But here's the caution flag, and it's worth being blunt about it. In this industry, operational is a word that's done a lot of work over the years, and it typically means the hardware is running and can be measured. Not that it's demonstrated error correction, not that there's an independently verified qubit count, and not that there's a fidelity benchmark you can put next to Q-Era's roughly 37 logical qubit machine at AIST and compare apples to apples. No independent qubit or fidelity figures were available at publication. What we have is press release language plus a roadmap, and that's simply what an early stage machine looks like before the hard proof arrives. And the roadmap itself is honest about that. Real quantum error detection and correction isn't promised until March of 2031, nearly 5 years out, which tells you the hard part, the part that actually decides whether anyone can trust this machine's output, hasn't happened yet. Compare that to what Q-Era and AIST already claim today, or to Microsoft and Atom Computing's Magne system chasing the same early logical qubit territory, and Japan's entry looks like a serious new competitor joining a three-way race that was already underway. And there's a nice wrinkle here for anyone tracking the neutral atom business case. The same 50-atom hardware Omori's team just turned on is effectively a customer reference for the company whose revenue we just talked about growing fast. If IMS's roadmap holds, and Shunkai actually opens up to outside researchers working on error correction, that's exactly the kind of external validation neutral atom bulls have been waiting for. Real government money, real lab hours, running on real Infleqtion hardware, outside the company's own sales pitch. For the non-specialist listener, here's the plain version. Think of this as Japan buying a seat at the table in a 3-team sprint to build a quantum computer that can actually correct its own mistakes, the single hardest unsolved problem in the whole field. Whoever solves it first doesn't just win bragging rights. They win the ability to run computations long enough and clean enough to be useful for things like drug discovery or new materials, which is the payoff everyone's actually chasing. Here's where I land on it. The physics behind this is genuinely good. Martinis doesn't hand out praise for nothing, and a 2 orders of magnitude speedup on the 2-qubit gate that's historically been neutral atom's weak point is a real technical accomplishment, not a marketing line. Room temperature operation, the ability to rewire which atoms talk to which mid-computation, an industry-academia pipeline with Hitachi and Infleqtion already bolted on. That's a full-stack machine built with commercialization in mind from day one, not a science fair demo. What it hasn't done, yet, is prove neutral atoms have leapfrogged the superconducting incumbents on the one metric that actually decides this race: error-corrected logical qubits you can trust. 50 physical qubits today, 10,000 with error correction by 2031. That's a plan, and a fairly detailed one, but it's still a plan. So here's my case. Real hardware, real industry backing, real physics behind the gate speedup, genuine national commitment stretching back to 2024, but 0 independent qubit or fidelity figures released today, a 5-year gap before the error correction claim gets tested, and operational doing the heavy lifting a press release needs it to do. Hype check on this one, a 6 out of 10. If today's episode helped you make sense of the neutral atom race, follow Quickly Quantum wherever you're listening, and if you know someone who thinks quantum computing is still science fiction, this is a good one to send them. This has been Quickly Quantum, an AI-voiced podcast, created and built by a real human using today's cutting-edge technology. Nothing you heard on this show is financial advice. I'm Brian Lampert, and I'll catch you all tomorrow. Take care.